Alright, we are recording, and I am in the corner again. The reason why is because I got another piece of real science news to share. Last time I shared some Berkeley Lab news that was concerning, well, the reason I was talking about it is not just it was really interesting, but because it covered how making new elements is really, really difficult. So in science fiction, when it's like, here's a new metal, and they treat it as though it's an element, or they say it's a new element, yeah, that's not really viable. That's very much the fiction, more the fiction than the science. In that video that I had done prior to covering the Berkeley Lab news, I talked about how alloys, however, make more sense in science fiction because we can, with currently existing elements, make new compounds, make alloys, make new materials, and from those can get the properties that we may want. That sometimes it's like, it's just science fiction, just new material, completely new element. It gives us properties, just like, or we could make it. And, well, this, as it happens, MIT did basically that, where they figured out a way to make a new material that can be used with nuclear fusion power plants, nuclear fusion reactors. More specifically, though, I think this would just be relevant or largely relevant for stellarators and tokamaks, which they both involve holding a fuel plasma, although in tokamaks it says actually two levels of plasma, versus the more like laser inertial stuff where they just have a target and they shoot lasers at it. That may still be relevant, but I'm not sure how relevant. They don't get into that, which is fine. So basically, in stellarators and tokamaks, you've got the fuel plasma, which is the hydrogen isotopes that you want to have fusion occur within. You have that as a plasma, so it's just very, very hot, and it's just going around in a ring. And you try to make sure there's enough energy and pressure there that eventually the isotope atoms that are just bouncing around, although they'd be ions in the plasma, instead of just going like this, they finally hit and fuse to release energy as nuclear fusion. Well, how's that energy carried away? One of the ways it's carried away is as neutrons, which makes sense because either you've got deuterium, which is one of the isotopes of hydrogen, which is one proton, one neutron. If you fuse two of those together, it's possible you get out an isotope of helium where it's two protons but only one neutron. The second neutron just went out like that. You might also be having deuterium fused with tritium, which has two neutrons, one proton. So that would mean that if it fuses together, you could have helium where it's two protons, two neutrons, and then again, you have a neutron going out like that. Now, ideally, that neutron is going to penetrate whatever material you're using to hold everything together, because you can't just have the fusion, the fuel plasma just sitting there. We are controlling it with an electromagnetic field produced one way or another. But you do need to have this all encased. You do need to have something solid surrounding it. Ideally, that neutron will just pass right through the casing and then hit the coolant on the outside that then absorbs that energy, and it heats it up to produce steam to turn turbines. And yes, so much of energy production on Earth is literally just boiling water. Just how it is. Anyway, what they've discovered, not MIT here, but just in general when doing this, is that the material that we usually use for the casing doesn't last that long, which is kind of weird because nuclear fission power plants, we use a material there that also neutrons pass through and all that. But there, the casing will last years and years. So why is it that when we do it with nuclear fusion, we're talking weeks or months or weeks in very short period of time? The reason that they explain in here is because the neutrons have so much more energy that when they're speeding through the casing, if they do in fact strike one of the atoms of the casing, there's a chance of it producing, they don't name it, but I'm pretty sure they are referring to alpha particles. This is one of the types of radiation. There's alpha particles, beta particles, and gamma rays. Gamma rays are photons. Beta particles are actually electrons. Alpha particles are the most massive. They are actually helium nuclei, so two protons, two neutrons. So the problem is, you've got the neutrons speeding through the casing material, which it's a little funny. I'm not sure why they kept talking about how it's mostly iron. I think they mean it's steel, which is an alloy of iron, so mostly iron. But they keep referring to iron, and it's like, okay. But it hits, you get the helium nucleus made, and eventually it actually becomes just a helium atom, so it gets the 2 electrons it needs to stabilize. Here's the problem, and for this I actually, unfortunately, they don't have a graphic here. I tried to make some that hopefully will make sense. Just let me turn this off. So here's the problem. You might not realize this with metals, but they actually are kind of like other materials, like even wood, in that there are grains. So something like this, where we've got, the red grain, green grain, and blue grain, essentially, and the border between them. Now, on its own, this is fine. But the issue is those helium atoms, which here I'm not bothering with the electrons, they like to... no, there we go. I forgot the layering. The problem is they like to collect in areas that they're most comfortable, which anything would, but it happens to be at the interfaces between the grains, which is a problem because you can have that happen. The helium atoms will actually wedge apart the grains, causing the casing material itself to fail. Now, why does this not happen with nuclear fission reactors? Because they also have to have casing materials that survive neutrons. The reason why that's explained in here is that nuclear fusion is so much more energetic. Those neutrons are flying through with so much more energy, there's a greater likelihood of them striking an atom and causing it to produce an alpha particle, which would mean that it has been radioactively damaged. It hit it and caused it to split. So minor instance of fission there. Okay? So, how do you solve this problem? How do you prevent this going to that? Well, what this research talks about is that instead of being like, well, let's figure out how to just shore this up, make sure that this damage doesn't happen, and it's like just stronger and better material, which is what I think a lot of science fiction authors would do. I'll admit it, maybe even I would do that. Like, if we could just come up with a way that were more amorphous, so we don't have the grains that... No, that's not the answer. Their answer is actually very, very intelligent. And I say that as in, like, this is brilliant. The problem isn't the helium atoms, essentially, is their solution here. It's where they are. It's the fact that it's at the grains, because that's where the helium wants to be. That's the most comfortable place for it to fall into. So, what did they do? They figured out that, well, what if we just add a material that the helium atoms are more comfortable falling into? So here, they're looking for helium-absorbing compounds. I'll leave it here. Let me put this, stepping back a bit, let me put it another way. Ice wedging, right? You have a crack in something, water flows into the crack, because that crack might be lower, like using my fingers here, there are the separations there. This is lower than the top of my fingers, so the water wants to collect in there, and if it freezes, it eventually separates and breaks things. So it can break stone, it can break roads, potholes, anyone? Basically what they figured out is instead of trying to figure out a way to get rid of the cracks, which is if we could make it really, really amorphous, and even then I'm not sure if that's possible. Hey, it's science fiction. Or some way to shore up across. No, they figured, all right, we'll just put in cracks here within the grains, more or less. They sought for helium-absorbing compounds, basically materials that can serve as new cracks for the helium to fall into. So instead of the helium, and I'm just going to turn it on here, instead of the helium falling directly into those interfaces, they fall in other locations. So they're not trying to prevent the helium from forming or prevent the helium from doing damage in total, but they're trying to control where it is. So it's in places that the damage is lessened, or it's not as big a deal. Mitigation by distributing the damage out, I guess is another way to put it, instead of specifically at those weak points. Yeah, it's really, really clever, and I do encourage you to read this. It's not a hard press release to read. I looked a little bit at the paper, which is linked to right here. I don't think you can see my cursor, but the paper, demonstration of halide formation for fusion structural materials as natural lattice sinks for helium. I did try reading that. Even the abstract was a bit much. I don't know how much of that is just, no, this is the terminology, we're stuck with it, and how much of it is we're writing jargon, but either way, that one, Did not get that. Didn't really grasp that one too well. But the MIT news item here that I am linking to, that is actually pretty easy to read. Do encourage you to read that. But yeah. So just kind of coming back to the thing that my original video was about, and probably what I'm talking about this one here is. It's amazing what we can do with materials we have around us today. You don't necessarily need to go to, hey, let's just invent a new element to solve some material science problem. It's like, no, we can just work with a new material. We can just invent a new material to solve the problems we have today. And by the way, I think I've started and stopped this recording so many times. I'm not sure if this counts as a new alloy of iron. They do make reference to iron because I'm sure the casing material is actually steel, but steel is an alloy of iron, so it's mostly iron. I'm not sure if what they're doing here would count as another alloy or just another material, because they're by putting in, it's actually iron silicate, as I recall, that they're putting in there. I'm not sure if that counts as alloying, which kind of makes some sense to me because you're putting it in there to have the property of iron silicate there, not you're putting in there to change the property, to change the characteristics of the whole material, which to my mind, which I don't know all this, to my mind, that's more so what you would expect with an alloy. It's diffusing through and influencing properties everywhere, whereas this is no, we're trying to have the properties of the material in the steel. So yeah, that's all. Yeah, that's all. I hope you found it interesting. You can certainly look up the MIT thing, read it yourself. It's very interesting, and see you next time.